Hi everyone, welcome to the Intro to Functions video. So first off, we're going to talk about how we can determine if a relation is a function. So first off, a relation is a function if every x corresponds to exactly one y. So basically what that is saying is that x's cannot repeat. Okay, we do not want our x's to repeat. So what we do when we have a graph is we're going to use the vertical line test. Okay, this is a graph is a function if any vertical line drawn through the graph intersects the graph no more than once, meaning it only touches the graph once. If it hits it more than once, it's not a function. So looking at the pictures that we have, I'm going to go ahead and zoom in. It says we want to say if this is a function or not a function. So if I'm looking at number 1, if I draw a vertical line here, it only hits my function one time. If I draw a vertical line here, it only hits my graph one time. So no matter where I draw a vertical line for number 1, it's only going to hit the function one time, which means this is a function because it passes the vertical line test. Okay, so now we're going to go ahead and move to number 2. So number 2, we have this circle. So if we draw a vertical line on number 2, notice how my vertical line hits the circle in 2 different locations. That means this is not a function. Since it is not a function, that means it fails the vertical line test. So this is because it fails the vertical line test. Okay, number 3, we have a piecewise function. So one thing I want to review before we talk too much about the piecewise function is that we see that we have open circles and we have closed circles. So let's talk about what these represent. So remember that open circles are excluded from the graph, meaning there is not an actual value at an open circle. If you see a closed circle, that means that it is included in the graph. So when I go to draw a vertical line here, although it looks like it's hitting 2 different spots, this right here is an open circle, so there is not a value there. Same thing goes if I were to draw a vertical line here. Again, that part right there, because it is an open circle, it is not included in our graph's values, so this would represent a function. Now, looking at number 4, I have a sideways parabola. So if I draw a vertical line, I notice that it hits in 2 different spots, which means this is not a function. So again, to determine if a relation is a function, you can do the vertical line test if you have a graph. If you are given points, a table, a mapping, you would just look for repeating x's that go to different y's. Next thing we're going to talk about is symmetry. So how can symmetry be determined graphically and how can it be determined algebraically? So we're going to start by talking about graphically. So graphically, we're going to look at the symmetry of the graph. So what that looks like is if it is an even function, that is symmetric to the y-axis. Okay, meaning if I fold it in half along this y-axis, everything on this left side right here is going to match everything on the right side. Okay, Another important feature that we can notice is that if I have a positive x, then I will have a negative x that has the exact same y values. So what that would look like on a table is if I had the points of -3, 9, -2, 4, -1, 1, 0, 0, 1, 1, 2, 4. So if we notice that I have a -2 and a +2, they both have the same y value of 4. I also have a -1 and a +1, and they also have the same value of 1 for the y. So that is another way you can tell if it is an even function. It is symmetrical about the y-axis. If we fold it in half on the y-axis, everything on the left matches everything on the right. Then we go to our odd functions. The odd functions are symmetric to the origin. Okay, so what that means is that it is symmetric about this point right here. So when we're talking symmetric about the origin, if I have something in the first quadrant like I do here, its symmetry partner is going to be in the third quadrant. If I had something over here in the second quadrant, its symmetry, or to be symmetric, it would have to be somewhere over here in the fourth quadrant. Okay, as far as our points go, if I have the x, y value, to know that it's an odd function and symmetric to the origin, both of my signs are going to change. So if I had a table, what we would look for would be if I have -2, -8, -1, -1, 0, 1, 0, 0, 1, 1, and 2, 8. So notice how I have a -2 and a +2, and my -2 has a -8, and my +2 has a +8. So the signs are opposite. Same thing applies for the -1 and the +1s. Okay, so all of the signs change. So that is how you would determine symmetry graphically. Now, looking algebraically, okay, algebraically, to determine the symmetry of a function, what we're going to do is you're going to substitute x with -x, and then you simplify. So if nothing changes and you get exactly the same thing that you started with, that means we have an even function. If all of the signs change, then that means that we have an odd function. If only some of the signs change and others don't, then it is neither. So we do have the option to have neither even nor odd. Okay, algebraically, something that you may see is that this right here that says f of -x is equal to f of x. Again, all that's saying is that we're substituting in -x and we're getting the same exact thing that we started with. Okay, that means nothing changes. It's the exact same thing. Or if everything's going to change, we can write it like this algebraically, meaning that if we plug in -x, then we're going to get the negative version of what we started with. So all of the signs have to change. So I have some examples that we're going to try. And it says just determine if the functions are even, odd, or neither. So at any part of this, you can go ahead and pause the video, give it a try, see what you think, and then watch the video to check your answers. So on number 5, we're going to start with f of x equals x squared. So I am going to evaluate it at f of -x. So when I do that, I substitute in -x for the current x given. It is important that you put it in parentheses. Parentheses will make a difference, and if we just make a habit of putting it in parentheses now, it's going to save us later. So now I have a -x squared, which is the same thing as -x times -x. Well, a negative times a negative is a positive. X times x is x squared. So notice how I got the exact same thing that I started with once I plugged in -x. So what this tells me is that my function is even. Since my function is even, again, when I plug in negative x, I get what I started with, which was f of x. And that's all we have to do right there. Okay, so this right here is just me making the connection to that algebraic notation that was above. Looking at number 6, we have f of x equals x to the third power. So I have f of negative x. Again, that's what we evaluate to determine if it's even or odd. So I plug in negative x, again making sure that I put it in parentheses with the exponent on the outside. So now I have a negative times a negative times a negative. Well, we know a negative times a negative is a positive, and then that positive times a third negative makes that an overall negative, and x times x times x is x to the third power. So this time, I did not get what I started with. Those are not the same things, okay? So what we notice is that my signs did change. My original function was a positive, and now my function, once I plugged in negative x, is negative. All of the signs changed. There was only one sign to change, but it changed. So since it changed, that means now I have the negative version of what I started with, and that tells me that I have an odd function. So this is an odd function. Okay, to connect it back to the algebraic notation that we had up the front, I could also write this as the negative version of f of x, which x cubed is f of x, and there's a negative in front of it. So again, this is just the notation that I have above. So looking at number 7, we have f of x equals x squared minus 5. So we're going to evaluate at f of negative x. When I do that, I plug in negative x for each x, like this. We know that negative x times negative x is a positive x squared. There's nothing that is going to affect that negative 5 because it is a constant, so therefore it stays negative 5. We ask ourselves, did we get what we started with? And yes, it matches up exactly. So this is our original function of f of x. So once again, it tells us that f of negative x is equal to f of x, which means we have an even function. Looking at number 8, we have f of x equals x cubed plus x. So again, we evaluate at f of x. I am going to plug in negative x. We're going to evaluate f of negative x. I am going to plug in negative x for each of my x's, okay? Each of my x's. So I have a negative x to the third power. So that's a negative times a negative, which is a positive, times a negative, which makes it an overall negative. And x times x times x is x to the third. Then right here, I have plus a negative, which is just the same as minus x. So what I notice, is it the same as what I started with? No. My original one had all positive values. My new one has all negative values, which means all of my signs changed. Since all of my signs changed, that means I have an odd function. You could also look at it as if I factored out a negative 1 or just a negative sign, I have positive x cubed left over plus x, and that would give me that negative f of x value, because this x cubed plus x is f of x based on that given statement above. So again, that is just a way to make a connection to the algebraic notation that I have in the notes above. Moving on to number 9. Number 9, we have f of x equals x squared minus x. So again, we evaluate it at f of negative x, which means I am going to plug in negative x for every x that I see in this equation. So negative x squared, a negative times a negative is a positive, x times x is an x squared. Then I have a double negative right here. So two negatives here and here turn out to give me one big positive. So plus x. I ask myself, did I get what I started with? Well, my x squared is correct, but I started with a minus x, and now I have a plus x. So those are not the same thing. Did all of my signs change? Well, in order for all of my signs to change, that means this first one right here would have to be a negative x squared, and it's not. So it's not what I started with, and all of my signs did not change. So therefore, it cannot be even, and it cannot be odd. So this would be an example of neither even or odd. This one is neither. It did not meet any of the characteristics to be even or odd. Looking at number 10, f of x equals 4x minus 2. Well, again, we evaluate at f of negative x. We plug in negative x anywhere we see an x. 4 times negative x is a negative 4x. And then that minus 2 is a constant, so it stays the same. Since it stays the same, we can see, does it start or does it end with what we started with? And it doesn't. Okay, those are not the same equations. Then I ask myself, did all of my signs change? If all of my signs were going to change, then I would have to have a negative 4x and a positive 2x. That's not what I have. So once again, this does not meet any of the characteristics, so it would be another neither. Looking at number 11, we have f of x equals x to the fourth power minus minus x squared. So again, we start by evaluating f of negative x. Well, f of negative x would be negative x to the fourth power and minus a negative x to the second power. Well, a negative x to the fourth power would be a negative times a negative, which is a positive, times a negative, which is a negative, and times another negative, which would make it a positive. So we would get a positive x to the fourth. This minus sign I'm just going to carry down, and then I'm going to evaluate my second one. A negative x to the second power would give me a positive x squared. Okay, now this minus sign right here just dropped down. So now that I've done that, I wanted to make sure that you understand that this right here is this. It did turn positive, but it has that negative in the middle. So it's really x to the fourth minus x squared. So we ask ourselves, did we get what we started with? This time we did. So therefore, since we got what we started with, nothing changed. That means it is even. This is an even function. Now, lastly but not least, we do need to make a correction on this. I did have a typo. That should be an exponent of a 5. So once again, we're going to evaluate this at f of negative x. That means we plug in negative x for every x value that we have. And I evaluate. So negative x to the third power is a negative x to the third power, plus a negative x to the fifth power is a negative x to the fifth power. So now I have plus a negative, which means I can rewrite it as just a minus sign. So I have a negative x cubed minus an x to the fifth. We ask ourselves, did we get what we started with? We did not, but we do notice that all of my signs changed. They were both positive, now they are both negative. So if you need to, you can rewrite it as a negative times x cubed plus 5. Oops, not plus 5, plus x to the fifth. Okay, we basically just factored out a negative, and that shows you that we have the negative version of f of x. Okay, so since we have the negative version of f of x, or because all of my signs changed, that means we have an odd function. So if you look through all of the examples we did, can you make a educated guess about a possible pattern that you may see with even and odd functions and their equations? If so, write it down, and you can always check with your teacher to make sure that that is the correct pattern. So if you have any questions, please make sure you write it down so we can help you out, and ask us in class the next time you see us. So have a great day, Rangers, and I will see you in the next video.